Okay, so next week we want to spend time with Hubble, and he'll come up here, and his discovery and what it means. And so that's what we're doing because it's like a monumental uh, moment in cosmology. But so we need some a little prep work to get there. So this is for that. We talked about spectroscopy before, spectrometry before that, and it's measuring the spectrum from elements. And it was used a lot by chemists in the 1800s. They don't use it anymore. They don't need to. Astronomers still need to do this though, because they can't. Chemists can take a little sample and put in what's called a mass spectrometer, and it'll tell the chemist what the makeup is. Astronomers can't do that because they can't get physical samples of what they're looking at. So they're still depending on this. And the idea is simple. If you have a gas, let's say it's oxygen, and it's glowing, the oxygen's glowing, it'll give off light. And if we put it through a prism or a diffraction grating, you get this out of it. It doesn't form a full spectrum of colors, from red to blue. It just has these colored lines in it, okay, which is interesting. If we take a same gas, let's say it's oxygen, let's stay with oxygen, and it's not glowing, but we shine a light through it and put it through a prism or a diffraction grating, we get the full spectrum, but with black lines in it, in the place where the colored ones were here. Because that one is glowing, it's emitting light. This is called an emission spectrum. And this one is not glowing, it's absorbing light. This one's called an absorption spectrum. So instead of giving off this light, let's do a brighter one, let's say the yellow one. Instead of giving off this yellow light, it's absorbing that yellow light. I think that's this one. Okay? Instead of giving off this, well, here it's giving off that colored light. Here it's absorbing that colored stripe. And it turns out that we can actually tell what element it is based on the pattern, because each element has like a fingerprint pattern that it's going to make. So if I looked at the sun, I'd get a full spectrum of color. And we'll do that. That's why the window's open. We'll get a full rainbow. But if we do just a hot gas, that's what we're going to be doing, hot gases, we'll get just these colored stripes. If we had a cold gas, I don't have that, but if I had a cold gas in a jar and shine light through it, I would get these black stripes. Okay. And they're like fingerprints, so each element's unique. Hydrogen is like the most popular one with astronomers because it's found everywhere. If you might have a lab in like college chemistry or physics, and they'll make you do sodium because sodium just has two little yellow stripes. That's it. It's kind of easy to find, and so they make you do that one. And you can see they're all different, and we'll look at these. I don't have sodium, but I've got mercury, neon, helium, and hydrogen. So if they're in again, this would be an absorption spectrum. So if we have a cold gas like in the atmosphere of a star and the sunlight shines through it, it would produce that spectrum, and we could look at the black lines and say, oh, that's that element or this element or whatever element it happens to be. They're even doing this for exoplanets. Exoplanets are planets outside of our solar system, and for the last 20 years, they've discovered like 3,000 of them. I mean, when I was your age, they hadn't discovered one. We didn't know of any planets outside the solar system, but now you guys have like a catalog of like 3,000 of them or something. And the idea is you would take the spectrum from a star with the planet, the star is shining through the planet's atmosphere, and you'd get this combined spectrum. And then you do the star when the planet is behind it, and then that would just be the spectrum for the star. and then you'd subtract, and so you'd have the spectrum for the planet. And we'd be able to find stuff we're interested in, like stuff that's indicative of life, like maybe carbon dioxide or water vapor or oxygen or nitrogen or some other gas, and see what the atmosphere of that planet is like. Now, they don't look pretty like this. This is sodium again with the 2 yellow stripes. They look like this. So just kind of wanted to let you know that they're not real pretty. They wind up being like this, where we wind up getting the yellow at the black stripes are that's sodium. All right. So what happens with what happened with Hubble? Hubble was taking doing spectrograms of the galaxies. And remember the Doppler effect? The Doppler effect, we'd studied it with sound. The Doppler effect with sound was, well, if sound source is coming at you, the frequency shifts to high. And if it's moving away from you, the frequency shifts to low. So, like a truck, remember the classic truck coming at you? So we go from high frequency to low frequency. High frequencies, it's coming at you. Low frequencies, it's moving away from you. Well, these guys do the same thing with light. But with light, high frequency is blue, low frequency is red. So the two ends of the spectrum, the red and the blue end. So the red is low frequency and the blue is high. And so Hubble found that almost all the galaxies looked at, the majority were shifted to the red. In other words, they were moving away from us. A few galaxies were blue shifted, means they were moving towards us. Okay, so blue light means you're moving towards you, and red light moving away. And so he did all these. What does that mean? Why would most of them be shifted red? A few shifted blue. Well, the few shifted blue are things like the Andromeda galaxy, which we're on a collision course with. Also, some of the local smaller galaxies, the dwarf galaxies that we're sucking them in, so they're moving towards us. Those are shifted blue. The rest are all shifted towards the red. So what does that look like? Well, here's the top one is the normal hydrogen spectrum. It's real distinct, and it's the one most popular with astronomers. You get one red stripe, and then nothing happens until you get to cyan, and then you get a blue stripe, and then a bunch of stripes down at the end. If it's moving away from us, all the galaxies that were moving away from us, well, a bunch of the galaxies were redshifted, and he had to figure out why. And those stripes are all still there. They're all the same stripes, but they're shifted. They've shifted towards the red. And some of the few galaxies that were moving away, or moving towards us, the stripes are still there, but they're shifted towards the blue end of the spectrum. In fact, these are so popular with astronomers, they're actually named. The first stripe is called the H alpha, and then H beta and H gamma. So what did that mean? Well, the conclusion was that, well, the galaxies, most of them in the universe, are moving away from us. What does that mean? Well, it means the universe is expanding. And that was Hubble's great discovery, and that's what you guys are going to play with that on Tuesday. And there's another conclusion from that also that we'll talk about on Thursday next week. Tomorrow's odd. Yes, tomorrow's an odd day.